Okay, let's turn this into a Python program. Now I've already done this, but I'm going to talk you through what's in the program. If you prefer reading code to watching video and listening to me talk, just have a look at the code yourself and try and figure it out. Now we have our equation. Force is given by this bundle of constants divided by mod r squared minus vzx minus vzy and vxx plus vyy as our three components. So let's code that up. Set up some constants, and I'm pre-computing that bundle of constants out the front to save having to do it every time we go through the loop. Then we're setting up starting conditions. I'm going to start the proton at position 1, 0, 0 and start off at velocity 0, 0, 1. So it's going vertically upwards in the z direction at a speed of 10 meters per second, and it starts off 1 meter from the wire. And I've given a current of 4 amps through the wire. Set the time step very small because I think this is going to act pretty fast. Okay, so we need from our equation the magnitude of r squared. So I just use Pythagoras to work that out. I don't bother working out the magnitude of r and then squaring it because we never need the magnitude of r, just the magnitude of r squared. Save a bit of calculation for every step. And then we've got our three components of the force. In x, it's minus the constant Vz times x divided by mag r squared, the constant we pre-computed earlier. Similarly for y, and for z it's got the Vx times x plus the Vy times y. So this is just the equations we had before. And then we do the updates. So the new Vx equals the old one plus the force times delta t over the mass, force over mass being acceleration, of course. Similarly for y, similarly for z. That gives us the new velocities. The new positions are equal to the old positions plus the velocity times dt, and time increases by dt. And then I'm saving the x and z coordinates, as that's the only place it's going to move. There are no forces in the y direction, no velocity there. And then plotting them out. So let's see if it works. Okay, it does work, and it gives a rather strange shape. So starting at 1, 0, and it does a loop. Now, as we said earlier, if it was a uniform magnetic field, it would just keep looping and looping and looping in the same place. However, in this case, as it comes down here, you're closer to the wire. The wire's off to the side over there, so the magnetic field is going to be stronger, so it's going to have a smaller radius of curvature, which means by the time it comes back, it's coming back a bit further forward. And coming back a bit further forward and a bit further forward, and so it's doing a moving spiral around. So that looks like a plausible sort of motion for a proton in the magnetic field of a wire, still getting close to the wire in a rather curling pattern. Let's check that our time step was small enough. So that's what we get there. I'm now going to change the color to red, leave the graph in place, and make the time step 10 times smaller. So this will take a little while to run. And here we go, and it plotted it on top so much so that I can't even see the green coming out. Maybe very slight tinge of green on one side, but it looks like making the time step is 10 times smaller made no real difference. Let's make it 10 times bigger than we started off and see if that makes a difference. Let's run that. It's a bit quicker. And now you're seeing it does make a little bit of a difference. So it looks like our original guess was about right.